This podcast is brought to you by LMU Munich.
Thank you, Dieter. Thank you for the generous introduction. I might get used to these introductions from you, and I might even believe them in the end. So it's a great pleasure to be here, and enormous honor. I'm very pleased. This talk will have three parts, which you can immediately see from the title. The first part I'll talk about symmetries. The second part I'll talk about duality. And then I'll put the two notions together, and I'll argue for something about the unity of physics. This is really the point that the funding agencies like to put us in boxes. This person does condensed matter physics, somebody else does particle physics or an experiment. But that's not true. We are all physicists. And I'll show how ideas from different branches of physics can help each other, and how there is input from one branch of physics to another, and how ideas merge. So we'll start from the beginning. So symmetries. This is the Taj Mahal. It's a very symmetric structure. It's quite beautiful. And physicists really love symmetries from very old time. And this has a long history in physics. Physicists first discussed symmetries of space and time. The words are the Galilean symmetry, Lorentz symmetry, Poincaré symmetry. They're all named after the people who invented them or worked on them. And they help us a lot, and they're very deep. We know that they lead to conservation laws, and a lot of physics really followed from these symmetries. They also appeared in crystallography. So this is in a sense similar to the previous symmetries, because one of the elements of these space symmetries that I mentioned before is translation. Translations in the three directions of space and time. And the crystal breaks that symmetry to a subgroup. And the whole study of crystallography has been very productive over the years. As we move to later parts of the 20th century, we saw the importance of isospin and then SU3 of Gell-Mann and Neyman. These are flavor symmetries, and they are quite wonderful because they give us information about how to classify the various particles. And this is a long and fascinating story, which I will not repeat here. The second part of the 20th century was really dominated by a different idea, whose roots are in the 19th century. This is the idea of gauge symmetries or local symmetries. So if you look in Maxwell's theory and you write things in terms of a vector potential A mu, and you can shift A mu by d mu of lambda with some lambda that depends on x. X is a point in space and time. And Maxwell's theory remains invariant under such a transformation. In Einstein's theory of relativity, general relativity, you can transform the metric in a similar form. And here also, the transformation parameter xc can depend on space and time. So that's what happens in general relativity. So this is different than the symmetries here. Here the transformation parameter does not depend on space and time. It's just a number. And here the transformation parameter depends on the position. So it's a much bigger symmetry. And these ideas were used later in the standard model, in color SU3, and in the weak interaction, SU2 times U1. So gauge symmetry appears to be everywhere. Gauge symmetries are also extremely deep. It's a huge symmetry, much bigger than the global symmetry, because we have a separate symmetry group element, a separate transformation we can perform in different points of space and time. This is a much bigger symmetry. At every point in space and time, we can make a separate transformation. So it looks better because it's a much bigger symmetry. It's also extremely helpful in making electrodynamics for the first time, and then other theories manifestly, gauge invariance makes them manifestly Lorentz invariant, unitary, and local, and therefore also causal. So we all want our theories, in a quantum theory, we want the theory to be unitary, we want the theory to be causal, because there are events that happen, we do something and that causes something else to happen. That's not manifest in the theory unless you break Lorentz invariance. Conversely, you can have locality and unitarity, but then you don't have, so either you have Lorentz invariance or you have locality and unitarity, and gauge symmetry in electrodynamics makes the two of them live together. So that's another aspect of the fact that the gauge symmetry is very deep. And it appears all over the place. This is a sign of this unity of physics appearing already in the beginning of my talk, the same principle of gauge symmetry appears in Maxwell theory. That's the first time, and its generalization in the standard model of particle physics. It later appeared in general relativity. It later appeared in various examples in condensed matter physics. I'm not going to talk about that. And it's associated with deep mathematics, the mathematics of fiber bundles. And that's the hallmark of a deep idea. The same idea appears in many different places, so it's obviously very deep. So when I went to graduate school, I was taught physics is based on gauge symmetry. This is the #1 principle of physics. And I believe this is still being taught. I think gauge symmetries are still being taught this way in graduate schools. But, and that's a huge but, I don't think so. So first of all, we have Gauss' law in electrodynamics, and there are counterparts of that in the other theories with gauge symmetries. And that tells us that the Hilbert space is gauge invariant. It's very important that everything is gauge invariant. So the entire Hilbert space is gauge invariant. So the Hilbert space, the states in the Hilbert space are not in representation of this symmetry. This is a huge symmetry, but it doesn't really act on anything. The Hilbert space is invariant under it. So what kind of a symmetry is it if it doesn't act on anything? So gauge symmetry is really not a symmetry. It doesn't act on anything. All the states are gauge invariant. All the operators are gauge invariant. So what is it? Well, gauge symmetry is not a symmetry. Instead, it's a redundancy in our description. It's not a symmetry that you say that you do the experiment here and you do the experiment in Hamburg, you get the same result. That's a symmetry. But here, it doesn't act on anything. Now, indeed, as a sign that it is just a redundancy, the way Maxwell equations are first described, the way they were written down by Hertz, they were written in terms of E and B. A doesn't appear. The vector potential does not appear in the equations. You don't really need this whole thing of introducing an A just to say that it's subject to some redundancy. So that's another sign that it's not a symmetry. Now, in the quantum theory, we know that the vector potential is extremely important. We cannot describe the quantum theory only in terms of E and B, because they are Aronoff-Bohm effects. And therefore, it's still very important. But it is still not a symmetry. Now, the redundant description, as I said before, is extremely useful. I'm not saying that gauge symmetry is not useful. It's a very useful concept. But from here, we see that it's not really a symmetry. So, saying more about that, mathematicians are not surprised by that. If you talk to mathematicians, they say, of course it's not a symmetry. This is something that we use to describe what we're doing, but it's clearly not a symmetry of anything. It's also manifestly true in some lattice constructions, especially in condensed matter physics. If you talk to condensed matter physicists, they will tell you, well, of course it's not a symmetry. We can just write the theory with the gauge symmetry or without, and there is no difference between the two. It's also manifestly true in some low-dimensional examples in quantum field theory, in continuum quantum field theory. However, so all this is true, but again, I want to emphasize that I'm not saying that this is not a powerful tool. It's an extremely powerful tool, but it's not a symmetry, and I will say a lot more about it soon. So this was the first part. I'll use the misnomer gauge symmetry because it's common and it's too late to change it, but just know whenever I say gauge symmetry, I really mean gauge redundancy. The next topic I want to discuss is the concept of emergent symmetries. This is a symmetry that is not there in the fundamental description of the theory, but it appears in the solution. It appears at long distances. So global symmetries, the first symmetries that we discussed, can emerge as accidental symmetries at long distances. So the original theory doesn't have the symmetry, but at long distances we write the Lagrangian or the Hamiltonian, and for various reasons it turns out that whatever we write that would break the symmetry has very small effect at long distances. So then call it an accidental symmetry. And here are some examples. So if it's not an exact if it's not there at short distances, it cannot be exact, so it's only approximate. And here are some examples. In the real world, parity and time reversal appear like good symmetries. These are good symmetries of the real world. They are not symmetries of the standard model. They are not symmetries of the standard model of particle physics, but as we go to low energies, or we look at atomic physics, the parity violation or time reversal violation are not that important. They have a tiny effect. And that they appear as accidental symmetries at long distances. The same thing is true for baryon number symmetry. The standard model has that as a symmetry, but we believe, and I'll say more about that later, that it's not a fundamental symmetry of the world. It's not a fundamental symmetry of the universe, and that's regardless of whether you believe in ground unification or not. There's a very strong argument that the symmetry is not exact, both theoretical and even experimental. And the related fact is that the proton cannot be stable. So these are examples of symmetries that are not there at short distances, but they appear at longer distances as emergent symmetries, as accidental symmetries. So in this slide, I discussed global symmetries. Now let's say the same thing about the gauge symmetries and contrast the two stories. Okay. And contrast the two stories. Are you so irritated that you already want to disconnect me? So going to the gauge symmetries, they can also be emergent. They are not there at short distances, but they can appear at long distances. But in this case, unlike the global symmetry case, they have to be exact. And the reason they have to be exact is that they're not symmetries. It's not a symmetry, it's a redundancy in the description. A redundancy is always exact. You cannot have an approximate redundancy. You can have a symmetry that is approximate, but you cannot have a redundancy that is approximate. It's either a redundancy or not. It's like being approximately pregnant. You cannot be approximately pregnant. So the first examples of that were in lattice systems, again, mostly in condensed matter physics. I alluded to that earlier in the talk. And in some continuum field theories in low dimensions, where you start from some theory at short distances that doesn't have any gauge symmetries, and you look at the answer, you see that it has some gauge symmetries. But in these examples, it's on the lattice, so you can say, well, it's an artifact of the lattice. And in this case, it happens only in low dimensions. And in low dimensions, you don't really have a photon. So if you don't have a photon, you don't have a massless spin 1 particle, then the main sign of a gauge symmetry, that there is a gauge field, there is a photon or a graviton, etc., is not there in these low-dimensional examples. So one can dismiss that. But we'll soon see examples in higher dimensions. So that's what I wanted to say about emergent symmetries. And the last thing, I want to put everything together in the context of a theory of gravity. So when we come to a theory of gravity, there are very strong arguments based on black hole physics that in a theory of gravity, there cannot be any global symmetries. And that's what I alluded to earlier when I said that baryon number symmetry cannot be an exact symmetry of nature, because in the context of gravity, there are black holes. Imagine there is a global symmetry. We can dump, say, protons on a black hole. They fall in, then the black hole radiates all its mass, or most of its mass, with Hawking radiation, and we can dump more and more protons in, and it will radiate everything out. So that by itself changes baryon number. And the only way that could be consistent is if the symmetry is only approximate. So there can be accidental symmetries, but they cannot be exact global symmetries. This is different when we discuss gauge symmetries. In the case of gauge symmetries, there can be gauge symmetries in the theory of gravity, and that's good because we see a lot of gauge symmetries in the real world. But these gauge symmetries are very special. The spectrum must include all possible excitations that are compatible with the symmetry. All possible electric and magnetic charges that are allowed by the symmetry must be present as excitations in the system. So in the standard model, for example, we have a U1 factor. And if we have a U1 symmetry, there ought to be magnetic monopoles. They haven't yet been discovered experimentally, but this argument shows that such magnetic monopoles must exist in nature. There might be very few of them in the real world, but at least in principle, they exist, and we can say, at least in principle, produce them by some collisions of particles. That's not a very likely process, but it's not zero. So such excitations must exist. So this is all I wanted to say about symmetries, and everything I said so far is really ancient. This is from decades and decades ago. I did not say anything that was not understood many years ago. So moving forward in time, I'd like to say a few words about duality. So changing direction a little bit, and we'll start with some simple examples of dualities. Simple duality, the simplest one is dualities in free theories, and they are easy to establish. This is my favorite example, the harmonic oscillator. So we write the Hamiltonian of the harmonic oscillator. P is the momentum, Q is the coordinate, K is this constant in Hooke's law, and M is the mass of the particle. So I hope that everybody in the audience has already seen that at least once. And we can do a change of variables here and map Q to P over the square root, and map P to minus the square root times Q. And you can notice that the Hamiltonian is mapped to itself. That's an easy exercise. Classically, this is a canonical transformation. In a quantum theory, if we map Q to P and P to Q, this is like doing a Fourier transform. So we can perform such a Fourier transform and transform the Hamiltonian of the harmonic oscillator to itself. That might look like overkill because the system is exactly solvable. Why do I need to do that? I need to do that because we see a lot of lessons from that in other systems that are much harder to analyze. So this is typical. So what we see here is that we can perform this Fourier transform, and it's typical in Fourier transform that if we have a particle that is localized in Q, then its wave function is spread out in P. And if it's localized in P, its wave function is spread out in Q. This is the Heisenberg uncertainty principle. And duality exchanges P and Q, and therefore it exchanges something that is very localized with something that is spread out. It exchanges something that does not fluctuate a lot with something that fluctuates a lot. And this thing will come back and back later in the talk. So going to a slightly more exciting example, slightly more complicated, and again, still free theories. We can prove all these things using Fourier transform. If we have a scalar field phi in 2 + 1 dimensions, it is dual to Maxwell theory. So this is F mu nu of Maxwell theory, the field strength. And if we just write epsilon mu nu rho d rho of phi, we can perform such a duality transformation. In the quantum theory, this is again some kind of a Fourier transform. And the vector potential A that sits here is related to phi in a non-local way. So we cannot write a formula phi equals something in terms of A, because we'll need to perform a non-local transformation. See, there's a derivative on this side and there's a derivative inside here, so if we want to write A equals something, we need to invert the derivative, and that makes it non-local. So the transformation from the degrees of freedom in the right-hand side and in the left-hand side is a non-local transformation. That's telling us already that something is highly non-trivial here. And let's look at the equations of motion. The equation of motion tell us these are Maxwell's equations, that we just hit this with d mu. That's automatically 0 on the right-hand side because of the epsilon tensor. And we also have the Bianchi identity. The Bianchi identity of F mu nu turns out to the Klein-Gordon equation acting on phi. So this is again something typical in duality. The simple equation, which is the Bianchi identity, becomes an equation of motion, which is usually harder to solve or harder to understand. And the equation of motion of F is trivial in the other side of the duality. Another example of that, and then I'll draw some lessons, is we go to 3 + 1 dimensions, and we can take Maxwell theory. Imagine there are no sources, so Maxwell theory without sources, and we can map the electric field to the magnetic field. This is a symmetry of Maxwell's equations. If you look at Maxwell's equations, you can, wherever you see E, write B tilde, and wherever you see B, write minus E tilde. In a more covariant way, write it this way. F mu nu is proportional to this F tilde with an epsilon tensor. And this transformation is, again, very much like the transformation we discussed before. It exchanges the Bianchi identity from here with the equation of motion of here. So in terms of Maxwell's equation, there are equations with the divergence and the equations with the curl. If you exchange E and B, the equations are exchanged. And in a more covariant way, this is what I just said. And the new vector potential, after we do the transformation, so the transformation is nice and local in terms of E and B, but it's not local in terms of the vector potential. So the vector potential before the transformation, the one that sits here, is related in a non-local way to the vector potential in the other side, A tilde. And most important is that the gauge symmetry that we started with, the gauge symmetry of A, which sits in here, is gone in the other description, and instead we get another gauge symmetry, the gauge symmetry that acts on A tilde of the vector potential in here. So we see that gauge symmetries come and go. We have two formulations of the same theory, the same Maxwell's equations. Both of them have a gauge symmetry, but it's a different gauge symmetry. In the example we had before, in 2 + 1 dimensions, we had a scalar field with no gauge symmetry, and it was dual to Maxwell theory, which has a gauge symmetry. So we see that gauge symmetry just come and go. We have one formulation with it, one other formulation without it, and even if we have two formulations with a gauge symmetry, it's not the same gauge symmetry. So continuing with these simple examples, in all these examples, the duality transformation is obviously right. We're essentially doing a Fourier transform, so we can actually prove it. And all of them have the same thing that I've already mentioned before, that small fluctuations in Q turn into large fluctuations in P, and small fluctuations in P map to large fluctuations in Q. So both descriptions are correct. We have two descriptions of the same physics. This is what duality is, two descriptions of the same physics, but the descriptions are different. And what looks like small fluctuations in one description is large fluctuations in the other description, and vice versa. So when you say that something is very quantum mechanical, what you usually have in mind is that everything fluctuates very rapidly. The fluctuations are large. Now we see that this is just a property of the description that you used. There might be another description of exactly the same system where things don't fluctuate very rapidly. So this is something to keep in mind. So going to slightly more interesting examples. The example that involve more subtle fields, here are theories that most of them we cannot solve. And the first example is the Kremer-Venier duality. This again can be established exactly in the Ising model. It's a property of the Ising model, and it has various descendants in higher dimensions, including some gauge systems. So this is a huge field of study. It was done many decades ago. Again, systems with a gauge symmetry are dual to a system without a gauge symmetries, and that's not a peculiarity of some simple theories like the free Maxwell theory, but these theories are much more interesting. And there are many more examples in 1+1 dimensions, especially in the context of bosonization, conformal field theory, and so forth. So summarize, trying to take a lesson from all that, in all these examples, the thing that is always true is that we have small fluctuations are mapped to large fluctuations, and large fluctuations are mapped to small fluctuations. And if we have some coupling constant in the theory, if the fluctuations are large, it means that the coupling constant is large or strong. If the fluctuations are small, it means that the coupling constant is weak. So we see that duality allows us to relate theories at strong coupling to theories at weak coupling. We can take a theory which has large values of h bar and map them to theories with small values of h bar. This is extremely useful. It's useful because we can take a system which is very quantum mechanical. The fluctuations are very large. It seems that the system is horribly and hopelessly complicated. For example, the theory of the strong interactions. Everything is strongly coupled. Everything is complicated. We don't know how to calculate things. But if we know such a duality transformation, we can rewrite the same system using weakly coupled degrees of freedom that are much easier to analyze. So this essentially gives us a solution of the problem. We have a problem of strong coupling, large h bar, large fluctuations. We can map them. We can map it to a problem with weak coupling, very small fluctuations. So duality, the other thing I want to press here is not only is it useful, it's also an intrinsically quantum mechanical phenomenon. This is something that the classical physicist will not be interested in. Because in classical physics, all we can do is canonical transformations. And that has been understood for centuries. This is a much more subtle thing, which goes far beyond what can be done in classical physics. This is an intrinsically quantum mechanical fluctuation that allows us to trade large values of h bar with small values of h bar. So I'd like to give some examples of more interesting situations where this occurs. The details will not be important, so don't pay attention to the details, but I do want you to pay attention to the general picture that will emerge. And this is duality in 3+1 dimensions. There is something called n=4 supersymmetry. Some of you might have heard about it. The details, again, I emphasize, are not important. But this is 3+1 dimensions. This is just like the real world. So we have gauge theories, very much like the theory of the strong interaction, very much like what we see in nature. But this theory is really scale invariant. It appears to be the same at all distance scales. And it's characterized by a gauge symmetry G and a coupling constant alpha, like the fine structure constant. I should add here that alpha was first introduced by Sommerfeld, so it's really appropriate to give this talk with alpha in the slide in these Sommerfeld lectures. So this is what characterizes the theory, and this is the theory very much like the strong interactions. In the strong interaction, this G is SU3, and this is alpha strong, which is measured, say, at the LHC. The details are a little bit different, but from afar it looks very much like the theory of the strong interactions. So it turns out that the theory with G and alpha is exactly the same as the theory with another group, G tilde, and 1 over alpha. So we see here that if alpha is large, as in the strong interactions, this maps the theory to a theory with small value of alpha, 1 over this large number. And this duality exchanges strong and weak coupling. It exchanges large and small fluctuations, very much like what I said before. And the gluons of this new description are the magnetic monopoles of G. So we saw before how duality exchanges electricity and magnetism, and the same thing is true here, except that this group G can be quite complicated. So again, the duality exchanges a strongly coupled problem that we would like to solve, a complicated problem, and it maps it to a weakly coupled problem, a problem that is easier to solve, using a different group. So it's not the original G. So the gluons of G tilde are composite in terms of the fundamental degrees of freedom. And their gauge symmetry is emergent. So this theory is a gauge theory, and it has some gauge group, G. But this one does not appear if alpha is large, if the coupling constant is large and the fluctuations are large. It's completely gone. Instead, a new gauge symmetry emerges. So here I say it again. We have a map from G and alpha to G tilde and 1 over alpha. And this duality is an exact equivalence between theories. So this theory is exactly the same as this theory. So it's like in the Fourier transform with the harmonic oscillator. When I did this Fourier transform in the harmonic oscillator, I rewrote the theory. I had the Hamiltonian, and I rewrote exactly the same Hamiltonian. It's an exact transformation of the theory. So I completely changed the degrees of freedom, but it's still, this underlying system is the same system. So the same is true here. And if we could solve this system, and we see the spectrum of states, spectrum of operators, compute correlation functions, whatever physicists are interested in, the results in the left are exactly the same as the results on the right. And if alpha is very large, the results on the left are very hard to find. The results on the right are very easy to find. So, for example, in electrodynamics, alpha of Sommerfeld is a small number. Right? I hope everybody here knows what alpha is. So alpha is very small. So in electrodynamics, it's pointless to move to a dual description because alpha is already small and it's easy to calculate. In the strong interactions, alpha is very large, so it's hard to compute, but instead we have another description which is weakly coupled. And what I really emphasize is that the gauge symmetry of the dual description is emergent. It wasn't there to begin with, and it just emerged out of thin air. It just came out. So we can ask ourselves, which of the two gauge symmetries is the fundamental one? The one of G or the one of G tilde? We have two descriptions of the same physics. Regardless of which one is more useful, the weakly coupled one is always the more useful one, but regardless of that, we have two different descriptions of the same system with two different gauge symmetries. Even the group as a group is not the same. So these are really different. And perhaps neither one is fundamental, because you can use either one or the other, but not both. So it looks like neither of them is fundamental. We also discussed two kinds of gluons in this theory. The gluons are the gauge fields of this strong interaction-like theory. So we had the gluons of G and the gluons of G tilde. And the gluons of G tilde, I said, are magnetic monopoles, composites made out of the gluons of G, and vice versa. So which of them is fundamental? We have two equivalent descriptions, and the particles in one description are composite of the particles in the other description. So which of them is more fundamental? The lesson from that is that the notion of an elementary particle is ill-defined. We have two different descriptions, and the elementary particles in the system are different in the two descriptions, and the physics is exactly the same. There is no experiment that would tell us this description is right and the other is wrong, because the two descriptions give exactly the same answers. And in particular, the notion of an elementary particle, which is the name of this field, it's the field of elementary particles, this notion is ill-defined. This is unsettling. There is another notion of duality. All the dualities we discussed so far are exact rewriting of the system. We have some Hamiltonian, we have some degrees of freedom, we change variables, we do Fourier transform or whatever you, And in the end, we find another description of exactly this, an equivalent description. Everything is exactly the same. There's a weaker form of duality, where the two descriptions are not exactly the same, but they're only approximately the same, and they become the same only at very long distances. So the Hamiltonian at short distances is some HUV. For example, it could be some system of electrons interacting through some Coulomb force, and there are some ions. This is a typical system in condensed matter physics. We have some ions and electrons, and the ions have special bonds, etc., etc. So that's what we see at short distances. At long distances, we have an effective Hamiltonian that describes what happens at long distances. And even the degrees of freedom are typically different. I'll soon give examples. And we have what we call a renormalization group flow from short distances to long distances. So here is an example of that, example I really like. Imagine you look at some water in the ocean, and there are some molecules of water, and the molecules of water bounce around. So this is the description at short distances. And they are described by some Schrödinger Hamiltonian that describes how these molecules bounce around. And there is water, and there is air on top, and there's gravitational field, and they attract each other and repel, and what have you. At long distances, the relevant degrees of freedom are not where the molecules are. Nobody cares about that. What people care about is the shape of the water. This shape of the water, and if there is a wave on the water, and there is an effective description. The degrees of freedom at short distances are the positions of the molecules. The degrees of freedom at long distances are the velocity field of the water. And the equations that describe that are the microscopic equation with Coulomb law between the molecules. And the effective description here uses Navier-Stokes equations. So we have two different descriptions. The fundamental description is here. Describes electrons and molecules, etc., etc. It's extremely complicated. At long distances, we have Navier-Stokes equation. Nobody knows how to make a change of variables from one side to the other, but we have no doubt that this is right. So this is very common in physics. We have two different descriptions, one at short distances, another one at long distances. And the description at long distances is the effective description, and it typically uses different degrees of freedom. Again, in the case of the water, these are the molecules, and the degrees of freedom here is the velocity field in Navier-Stokes equation. So there are many examples of that, and sometimes we can easily identify the long-distance degrees of freedom, and sometimes we cannot. So for example, in Ginzburg-Landau theory of superconductivity, we have the fundamental degree of freedom in this effective description is the Cooper pair field, and it can be thought of as a bound state of two electrons. That's true in superconductivity. In QCD, the theory of the strong interactions, at short distances we see quarks and gluons, and at long distances we see a theory of pions, and we can think of the pions as being bound states of two quarks. So this is an example where the degrees of freedom at long distances are relatively simple in terms of the degrees of freedom at short distances. But this is not always the case. Sometimes the degrees of freedom at long distances are related in a non-local way to the degrees of freedom at short distances. For example, there are many examples of emergent gauge symmetry. I'll give more of them soon. There's something called particle-vortex duality in 2+1 dimensions. It appears first in high-energy physics and in condensed matter physics. This was in the 70s, I guess, late 70s. And there are emergent gauge fields in the fractional quantum Hall effect. And these gauge fields here and here are very mysterious because they are not related in a simple way to the fundamental degrees of freedom. We cannot write a formula. The gauge field at long distances equals something in terms of the short distance degrees of freedom. The relation is much more subtle and therefore much more interesting. I'd like to spend one slide summarizing what can happen in gauge theories in 3+1 dimensions. So at short distances, we have some gauge group G, very much like what we said before, and there might be some quarks, and there might be some story like in the strong interactions. And then, depending on the details of the theory, there could be different things at long distances. One thing that can happen is the theory can be infrared-free. So at long distances, we find a theory based on the same gluons and the same quarks, these are the degrees of freedom, but the interactions become weaker and weaker as we go to long distances. That is the case, for example, in QED. In QED, at long distances, we see just the photons, and they interact very weakly. The second thing that can happen, there could be a non-trivial fixed point, or a critical point, depending on which culture you come from. And this is an interacting scale invariant theory, like the one I mentioned earlier. In this case, the notion of a particle is not even well defined. There can also be an approximately free theory of bound states. Example, QCD, the theory of the strong interactions, has pions at long distances, and the pions are weakly coupled, but they are there, and we can understand them and describe this physics. And we can also have an empty theory, possibly with topological order. This is a hot field in condensed matter physics, understand all possible gapped phases of matter. And all of these options can be realized in various examples with gauge theories. Just by dialing the gauge group, dialing the number of flavors, changing the parameters, we can scan all these options. So all these options are realized in QCD, and that's what people understood already long time ago. A little bit later, but still long time ago, a similar story arose with something called n=1 supersymmetry, where one could cast this whole story in terms of duality. So we have here two different theories. One of them we'll call electric, and one of them we'll call magnetic. And I wrote them in kind of purple or whatever. That's the ultraviolet. And at long distances, they can flow to a non-trivial fixed point. This is something which is called the conformal field theory. Alternatively, we can have some electric degrees of freedom at short distances based on G. And at long distances, we find a theory based on G tilde. This is a much more interesting situation, because at short distances, we have what appears like the fundamental degrees of freedom. And they are based on some gauge group G, and there are some quarks and gluons and what have you. And at long distances, we see another theory with other gluons, which are bound states of these gluons. The gluons here cannot be written in a simple form in terms of the gluon here. The transformation between them is non-local. But unlike the previous examples I mentioned with non-local transformations, we cannot perform it explicitly. Yet we have no doubt that this is right. And so we start at short distances with one gauge group. We end up at long distances with another gauge group with a totally different gauge group. So the gauge symmetry here is an emergent gauge symmetry. It's not visible at all in the ultraviolet degrees of freedom. And therefore, we say that gauge symmetry is not fundamental. Since this is important, I'd like to summarize it again. So at short distances, we have an asymptotically free theory based on G. And at long distances, we have a theory, again a free theory, but now based on G tilde, totally different degrees of freedom, totally different gauge symmetry. So unlike ordinary QCD, where at long distances we see pions, here at long distances we see some kind of a QCD tilde, some other version of the same theory, but with different gauge group, different gauge fields, different quarks, etc. And as I said before, the gauge fields of G tilde are composite, and their gauge symmetry is emergent. So there are many more examples of that, and by now we know that duality and emergent gauge symmetries are ubiquitous. They appear in condensed matter physics, tons of examples. They appear in the study of high energy physics, tons of examples, and I'll soon also mention that it appears in string theory. So these ideas of gauge symmetry, so of a duality, and coming with that, the idea of emergent gauge symmetry are extremely ubiquitous in physics. Again, the sign of the unity of physics that the same ideas appear in different branches. So if you're a high energy physicist and you have a friend who is a graduate student in condensed matter physics, you might be doing exactly the same thing. And I'll demonstrate it more in the third part of the talk, when I talk about, put all these dualities together and say more about the unity of physics. I would like to put one slide about I mentioned earlier general covariance as another example of gauge symmetry, but now we know that it also can be emergent, and that there are many examples in string theory. This is a huge topic, more than just one colloquium, but I'll just mention it here on one slide just for completeness. I mentioned so far a duality between two field theories, but we could also have various dualities between two different string theories. It's called string-string duality. I'm not saying anything here except that they're called T-duality, S-duality, and U-duality, not very informative names. And there are also string field dualities, which are much more interesting. These are dualities between field theories and string theory. And these are various examples that came over the years. This is an extremely hot topic these days, and a lot of activity with a lot of progress. But I want to take the talk in a different direction. And I want to talk about the duality between bosons and fermions. Now, when we studied quantum mechanics, we were told that the particles in nature are of two kinds. They are bosons and fermions, and they are really different. The bosons satisfy Bose statistics, and the particles have integer spin. And the fermions satisfy Fermi statistics, and the particles have half-integer spin. And they shouldn't be confused. Some particle is either a boson or a fermion. It cannot be both. But there are examples where a system of bosons can appear like a system of fermions, and a system of fermions can appear like a system of bosons, very much like in this whole duality, except that here we start with a boson, we end up with a fermion, and vice versa. So the first example is what's known as bosonization in 1+1 dimensions. This is a theory of fermions equivalent to a theory of bosons. But that you could dismiss as not very exciting, because in 1+1 dimensions, the statistics is meaningful, but you cannot really talk about the spin of the particles. Even if the particle is massive and it sits at a point, space is just one direction, one dimension, and there's nothing to turn around. So we cannot really discuss the spin of the particles. You can say, well, this is a peculiarity of 1+1 dimensions. In 2+1 dimensions, massive particles can have spin. So it's a little bit more interesting. Massless particles have no spin, but massive particles can have spin. And indeed, in the 70s and 80s, there was a phenomenon known as spin and statistic transmutation in 2+1 dimensions. Takes a massive particle, you couple it to a gauge field with some special interactions. These are Chern-Simons couplings. The details are not important. But using the coupling to gauge fields, you can turn a boson into a fermion or the other way around. And that has been extremely powerful and useful in the context of condensed matter physics, and the word that comes to it is flux attachment. It's very popular in the context of the fractional quantum Hall effect. So you take a boson, you attach some flux to it, and it behaves like a fermion. And it had integer spin, you attach the flux, and now the spin is half integer. Or the other way around. You can take a fermion with half integer spin, you attach flux to it, and it becomes a boson. So this smells a lot like a duality. We have two different descriptions. We have a bosonic description and a fermionic description. These are different descriptions, but we describe the same physics. So over the last 5 years or so, there's been enormous activity in this field. And throughout the talk, I did not give references, because I could just give slides after slide after slide of references of all the tens of thousands of people who made important contributions here. But since this is recent development, I decided to put some of the papers. I'm sure you can see all of them, at least Ronnie, who probably figured in all the different activities here, and I'll mention that in more detail now. So people found now many new dualities between bosons and fermions in 2+1 dimensions, and the structure of the slides is very much like what I showed you earlier. You start at short distances with a theory of bosons coupled to gauge fields, or a theory of fermions coupled to gauge fields. So this is the theory at short distances. This is another theory at short distances. These two theories are really different, because here we have bosons, here we have fermions. These two theories are easily distinguished between one another. But they both flow at long distances to the same non-trivial fixed point. And this non-trivial fixed point could be extremely interesting. So there are tons of examples of this now. Much more interesting is the following situation. We start at short distances with bosons plus gauge fields, and at long distances we end up with free fermions. So that kind of goes against the intuition we all have. If we have some bosons, all the particles have integer spin, let them interact as much as you want. How can they possibly have half integer spin in the end of the day? Well, they can do that. So we have many examples where bosons with gauge fields become free fermions at long distances. This is interesting, because the system here is extremely complicated. This is some field theory with strong coupling and large quantum mechanical fluctuations. This is as complicated as it could be. And yet, we know what the answer is. The answer at long distances is a theory of free fermions. So why do we think this is right? And here I find the sociological argument at least as interesting as the physics, because it's really an amazing story. The story started with particle-vortex duality that I mentioned earlier, which was in the late 70s. So that came from particle physicists and condensed matter physicists. Now, people also found dualities in supersymmetric theories. Dieter mentioned some of them in his introduction. And over the years, these dualities can be almost proven. This cannot be proven, but there have been enormous amount of evidence that this is right. There were many tests. They are highly non-trivial tests. Nobody has any doubt about that. There was also the topic of string duality, which is a cousin of this, or maybe I should say a precursor or a descendant, depending on how you look at it, with, again, enormous body of evidence suggesting that this is right. None of that was proven. This was not proven, and this was not proven, but we have no doubt that these things are correct because of the amazing amount of evidence. And we had this ADS-CFT and large N, and all these things, which were almost independent line of investigation. Oh, and I should finally say there were some suggestions in the condensed matter literature. And independent line of research converged on the same picture. How did it happen? So there were some particle vortex dualities. This is a duality between fundamental particles and vortices that things turn around. That's from the 70s. This was extended in various directions. There were dualities in supersymmetric theory, a totally different line of investigation, which was motivated by different things, eventually led to string duality, and then back from string duality we found more dualities in supersymmetric theories. This was done mostly by different people who did not pay much attention to this. Another group of people worked on ADS-CFT and large N, and this is a story where you have some theory in the bulk, which includes gravity, and that is equivalent to a theory on the boundary which has no gravity in it. And there were some examples of different boundary theories with the same bulk theory. If the bulk uniquely determines the boundary theory, and if we have different boundary theories leading to the same bulk theory, it must be that the two theories on the boundary are dual to each other. That was the reasoning, and that suggested some dualities, and these dualities could be checked at large N. And again, very few people knew both about this and about that. I meant knew all the details. It turns out that these ideas from people doing field theory and these ideas from people doing mostly string theories, these are mostly different people, meshed nicely with suggestions in the condensed matter literature of people who never heard of ADS-CFT and large N, never heard of supersymmetry, and they all were talking about the same thing. And ideas from different branches of physics converged on the same set of suggestions, which are precisely the dualities between bosons and fermions I mentioned earlier. This is a fantastic example of different branches of physics influencing each other. There are many other examples in the history of physics, but this is something that is good to keep in mind. If you want to specialize in high energy physics, don't dismiss the condensed matter physics course. And if you want to be a condensed matter physicist, don't dismiss the quantum field theory and maybe even the string theory course, because you might get new insight from there. So going back to these newly discovered dualities, there are many checks and relations which make us believe that it's actually right. First of all, if we assume this is right, we can derive many other dualities that had been checked before and has been shown before to be right. I've already mentioned that it was related to other conjecture dualities, which subjected to many tests. So if you assume the supersymmetric dualities, which were subjected to many tests, you can break supersymmetry and flow to a non-supersymmetric duality, and if the flow is smooth, this is an assumption, you land on these dualities. So it's not completely independent. Also, fantastic relation to mathematics. It's related to a topic in mathematics called mirror symmetry, and through a totally different line of logical line, it's related to something called level rank duality that mathematicians are interested in. These are rigorously established facts. You can derive these rigorously established facts assuming these dualities we just talked about. And the dualities are not independent. If you assume some of them, you can derive the others. If you assume another subset, you can derive the others. So in the string community, this is known as a web of dualities. We have lots of assumed dualities. Theory 1 is the same as theory 2. Theory 2 is the same as theory 3. Now there's another duality between 4 and 5, but it follows if you assume the duality between 1 and 2. So there are lots of connections between them in such a way that if some of these dualities are shown to be wrong, most of the web would disappear. So every time you test one of these dualities, you get more confidence in the whole entire structure. And after a while, you just believe it all. You should keep doing it. You should keep checking it, because it's always interesting, and it's always surprising how these things work. As I said before, it's a theory of boson giving out free fermions. This is shocking. But it turns out to be, it appears to be true. And that not only is it true, it also has applications. And the main applications I want to mention is in condensed matter physics. So these dualities have applications. The first is in the context of the fractional quantum Hall effect. The second is in the physics of first Landau level at half filling. You see, these are totally different topics. And the gapped phases of topological insulators and topological superconductors. So see how amazing it is. We start with ADS CFT in 10 dimensions and something called Vasiliev theory. I'm sure very few people in the audience heard about it. And that's a bulk theory, and it has two different dual descriptions on the boundary. These two dual descriptions must be the same. That's true at infinite n, so it must be true also at some large enough n. You substitute n equals 1. You land on your feet, you check it still works, and lo and behold, you connect to the physics of the first Landau level at half filling. So the fact that this has something to do with Vasiliev theory and string theory, I find that amazing. And there are probably many more applications. I would like to, for our end, make an analogy between symmetries, kind of putting a lot of the pieces we discussed, putting them together, and talked about symmetries in quantum gravity, talked a little bit about condensed matter physics. I would like to make an analogy between them. So both in quantum gravity and in condensed matter physics, there are really no exact global symmetries. We have a system of electrons and some ions and they vibrate and so forth. There are no exact global symmetries. Every global symmetry you get at long distances must be approximate. The reason is that you start from the original Hamiltonian. It doesn't have any global symmetry. So any symmetry you'll get at long distances must be approximate. So that's in condensed matter physics. In gravity, it follows from the physics of black holes. For gauge symmetries, the situation is different. There can be emergent gauge symmetries. They are very common. They could be in condensed matter. It could be in condensed matter physics, and they could be in the context of gravity. And in both cases, you can argue that all allowed charges must be, there must be excitations with all allowed charges. So if you have some gauge symmetry, and there are some magnetic and electric degrees of freedom, you must have monopoles with all the allowed charges. They must exist in the spectrum. I find this analogy quite surprising, because the reasoning in quantum gravity and in condensed matter physics, the reasoning is totally different. The reasons for that are totally different. And yet, we find ourselves in exactly the same framework. All the can be emergent global symmetries, but they are approximate. There can be emergent gauge symmetries, but then all the excitations must be allowed. They might be heavy, but must be allowed. So let me summarize the talk. We talked about a lot of things, so let me just enumerate them. We talked a little bit about symmetries, and we saw that symmetries are common in physics. Different branches of physics, they all use symmetries. And I made this analogy between symmetries in gravity and in condensed matter physics, and that's one example of the unity of physics. No exact global symmetries, and there can be emergent gauge symmetries, but all charges must be present. So that's a summary of symmetries. We talked about dualities, showed different kinds of dualities, and again, they are common in physics. This is a situation that two or more different descriptions of the same physics exist. One of them might be more useful than the other. The example of the system of bosons with complicated interactions becoming at long distances free fermions, the free fermion description is simpler to use because the system is free, but sometimes the complicated description is also useful. So this is the idea of duality. We also talked about the unity of physics. I think I try to make the case that insight from different branches of physics can help each other. And a recent example of that is this duality between bosons and fermions, and there are other boson-boson dualities and fermion-fermion dualities in 2+1 dimensions. And that has led to better understanding of known phenomena and mechanisms, and also pointed to new phenomena and new mechanisms. Another lesson of the talk is that gauge symmetry is not fundamental. We saw that gauge symmetries can come and go. I even emphasized that we shouldn't even call them symmetries. They are just kind of a useful tool, but not more than that. And it's also, they are extremely useful to make Lorentz invariant unitarity and locality manifest, but they should not be viewed as fundamental. And one way to see that, there could be different such dual descriptions which have different gauge symmetries. I would like to take that lesson from that to make a bold suggestions. I've made it in the past, that we shouldn't be surprised by these dualities. We talk about this duality, and it always looks amazing. How did it happen that we got a new gauge symmetry out of nothing? How did we get fermions out of bosons? How do we get bosons out of fermions? How did this whole thing manage to be consistent? And we are amazed. If we are amazed by something, it means that we don't understand it. So my lesson from that is that we don't really understand field theory, and we should look for a reformulation of quantum field theory, which makes dualities manifest. I'm not saying that the current understanding of quantum field theory is wrong. All I'm saying is that it does not do justice to the beauty of the theory. And that's really for the younger members in the audience. If you look for a good challenge, this is a good challenge. This is a good problem to work on. So I'll stop here. Thank you.
All right, thank you very much, Martin, for your beautiful talk. I think we still have time for questions.
If I understood you correctly, you said that duality is entirely quantum phenomenon.
Yes.
And as a condensed mathematician, let me disagree with you and give two examples. First one is 2 plus 0 isn't model, which is self-dual. You may argue one map can map high temperature regime to low temperature. I understand we can say that 2 plus 0 is equivalent to 1 plus 1, and therefore it's quantum. But with a second example, with a two-dimensional turbulence, where you have a duality of a direct cascade to inverse cascade, you don't have this argument anymore. And this is entirely classical.
Okay.
Could you please comment on that?
Yeah, I certainly can. So I cannot comment on the second one because I don't know anything about it. There are examples of canonical transformations which look like duality, and I have nothing to say about that. And it's true that 2 plus 0 is 1 plus 1. It's actually a lot deeper than it sounds. But if you think of it as 2 plus 0, you still invert beta, or whatever, beta minus beta critical. That's the same as saying that it's intrinsically quantum. You can always say that any quantum system can be viewed as classical statistical mechanics in one dimension, or this is saying that 3 plus 1 is like 4 plus 0. That's true, but it's still quantum that it's only true if you have to do some kind of a functional integral. You have to sum over degrees of freedom. It's not, the duality is not true configuration by configuration in the functional integral. So even in your quote-unquote classical system in 2 plus 0 dimension, you do not map a particular configuration of the spins is not mapped to another configuration of the spins. It's much more subtle than that. You map, and indeed when the configurations of the spin do not fluctuate rapidly, it is mapped to something that does fluctuate rapidly. And if these fluctuations could be either quantum mechanical or statistical mechanics fluctuations, but they're still fluctuations. In that sense, I'd like to think of it as quantum. It depends on where you grew up. I grew up in zero temperature quantum field theory. And there it's an intrinsically quantum phenomenon. I think we both agree, we can argue about the words, but you agree that it takes something with small fluctuations to something with large fluctuations. That's what happened in the Ising model. I'm not familiar with the turbulence.
You know, 2D turbulence is not conformal, but nevertheless it's dual. So there are inverse cascade in K-space, there are direct cascade in K-space in inverse, and they're dual. And this, to me, it's entirely classical phenomenon.
Okay, I'll be happy to learn more about it.
Yeah. Sorry. You said that the U1 factor in the standard model requires also that there should be a dual charge to it, right?
Yes.
So this means hypercharge has a dual counterpart.
So hypercharge is the U1 charge.
Yes.
I said that there must be magnetic monopoles of that U1 factor.
This is, so to speak, the counterpart of the hypercharge.
I don't know what you mean by counterpart.
Dual counterpart.
The dual counterpart in the sense of dual, yes.
Is not electric.
You can say that think of hypercharge as being electric. There should be a magnetic version of hypercharge.
Does it
And
mean-
indeed, in theories of ground unification, you can prove that this thing exists. Because you can really write it down.
So does this mean that the Fermion content of the standard model is incomplete because this is not this requirement is not met by the?
That's correct. That's correct. But this is a property only if you only if you couple it to gravity. Without gravity, there is no problem. Without gravity, you could say that the model makes sense as it is, and you don't need to add any magnetic monopoles. If you have, you need gravity. If you have gravity, you can prove that all the charges that are allowed must be present. And since a magnetic monopole is allowed, so what's the argument? The argument is if you have a magnetic monopole, what determines its magnetic charge? This is Dirac's story. You try to create a Dirac string attached to it and tune the magnetic flux of the Dirac string such that it's not visible by any of the electric charges in the problem. So you ask yourself, is there a solution to this equation? Is there a value of the magnetic flux such that no particle in the standard model would detect it? And the answer is yes. There are such things. And if there are such things, such excitations must exist in the spectrum. They might be very heavy, but they must exist. And that's where you use gravity. It's basically you can spread the magnetic field on the horizon of a black hole, and there's no way to exclude that. That's a way of saying. There are other ways of saying the same thing.
Okay.
But yeah, it's not saying that the standard model as a quantum field theory without magnetic monopoles is inconsistent. That's not what I'm saying.
And it does not mean that there should also be quarks having magnetic charge instead of electric.
Well, there could be a whole very rich spectrum of dions, of monopoles and monopoles with both magnetic and electric charges. There's a lot. Usually, the allowed charges are in a lattice, and there should be excitations for every point in the lattice. The entire lattice has to be populated. You see, once you have a magnetic monopole, you can always take any one of the particles that you know about, say an electron, and throw it on the magnetic monopole, and then you have a diode. It doesn't have to be a bound state. It doesn't have to be a single particle, but there are states with these quantum numbers.
Questions?
And so in the duality between the group G and G tilde, does these two groups have to satisfy some conditional relation, like they are small pieces of a large group? Or
No. Yeah, so it's a very specific map. For every G, there is a G dual. For a mathematician, I would say this is the Langlands dual of that group. So it's a well-defined group, but it's not the case that you can embed both of them in a bigger group, because the degrees of freedom of one group are non-locally related to the degrees of freedom in the other group. There is no description of the system where both gate symmetries are present. There are two descriptions, one with G and one with G tilde, and you can take your pick, and both of them are equally good or equally bad. But both of them are valid. One of them might be easier to handle, but both of them are correct descriptions.
You said that a bosonic system can look or can behave like a fermionic system. Can you explain a bit how that works?
Well, for massive particles, it's more or less, well, it's understood for decades. It's still surprising. Take a particle and you attach magnetic flux to it. Then a fermion can become a boson. In fact, this is something that, who is teaching quantum mechanics here? This is a great exercise for quantum mechanics. You can give that to your students. So you take a magnetic monopole and you say that there's magnetic field around it, that of a magnetic monopole. So there's B equals whatever it has to be of a magnetic monopole. And you take a particle with charge E and you put them together. And it turns out that there is non-trivial angular momentum in the electromagnetic field between them, which is E times G. The magnetic monopole has charge G, and the electron has, or the particle, the electric charge of the electrically charged particle has charge E. Then E times G has to be an integer. This is Dirac quantization. And the angular momentum of the system is E times G over 2. So you can take a bosonic magnetic monopole and a bosonic particle with charge 1, both with charge 1. You put them together, you get a fermion. This is a beautiful exercise in quantum mechanics, and I encourage you, Dieter, to teach it in the class. If you don't know how to solve it, give it to them as a problem.
Yeah, that's in fact one of my basic strategies often. I cannot solve something, I ask the student to solve it.
So this is something that is very old. Okay, and there are variants of it. If you just take one massive particle and you put flux on it, you can change its spin from integer to half integer in a similar way. What's non-trivial here is that it's true also for massless particles. So the story before was very first quantized. Take one non-relativistic, one massive particle, take another one, and you do just ordinary quantum mechanics. When the particles become massless and they fluctuate rapidly, and their number is not well defined, and you have all the complexity of second quantization, it's a lot harder. And then we do not know how to prove it. So we don't know how to prove it, and that's why it's more amazing. Always, when you can prove something, you're no longer amazed by it, because, oh, you can just follow the algebra and check. You're surprised when there's a result, you didn't expect it, and you have no way of proving it. So this is in this category, and that's why I like it.
Okay, are there more questions?
Would you consider a percolation transition as a duality?
A very interesting thought. I think it falls in the same category as turbulence in the sense that I don't have anything intelligent to say about it.
Well, I mean, there is an example, for instance, in 2 dimensions percolation on a triangular lattice where the percolation threshold is exactly determined by the zeros of you would call it a Gauss, how do you call it, churn number. So this has a great similarity with the transition in the Ising model. You can map this on transition on Potts models or Ising models, and it is a topological transition. So you can consider that.
Well, I didn't consider it not because I don't think it's right, but because I know nothing about it. And if I read more about it, I might need to rewrite my talk and include it in the list. I'll be very interested in hearing more about it. Whatever it is, it clearly demonstrates my point about the unity of physics, is that there are either other things in physics that I'm not familiar with, either percolation or turbulence, that fit this story. So it only reinforces my point about the unity of physics. This is the only semi-intelligent thing I can say about it. I wish I could say more.
All right. Let's do more questions or remarks or complaints. So that I see them.